Okay, welcome back everybody to, what is it, day 5 of Math 365 partial differential equations. Today's class has a clear singular purpose. I want to show you not just D'Alembert's solution to the wave equation on the entire real line, but also how to derive it. So one thing that we could do in this class is have me simply give you the formula, which I have shown you before with the form of like an optional exercise, and then immediately just pass to discussing solutions, and then going to the situation of boundary values. But looking over this proof, it's actually so interesting. It's kind of like a wonderful tour de force of calculus, and it's also a nice application of using the method of characteristics to solve a second order ODE. So I really want to show it to you. So I'm going to. And I hope you enjoy it. So you've already kind of been primed for this argument through questions 3 and 7 on your homework, where you instituted a coordinate change in order to facilitate you solving an equation. So we won't literally be taking that tack. We won't be operating in the characteristic coordinates, but we will use heavily the method of characteristics to get this to work. But without further ado, let's just go straight into it and see what we can do. So we're looking at this classical wave equation, and we've seen in the last class how to derive this. So C is the propagation speed of the wave speed, and we're going to be assuming that C is a constant. And to solve an equation like this, you do need initial conditions, and here are the initial conditions that we're going to impose. So what we're doing is this solution due to D'Alembert is on the entire real line. So this is like a vibrating infinite string. It's a little bit more nuanced to handle the case where you have a string with fixed endpoints. We'll just do that in this. And so the initial conditions that you should put, well, for a second order ODE, if you remember that class, you did, for second order, you had two conditions, like initial position and velocity. The analog of that here is your initial position is now a function of x along the entire x-axis. Your initial velocity is the time derivative of uxt, but the time derivative here at time 0. So you've got an initial position of that string, and you've got an initial velocity of that string, and you need to be expressed as or what have you. And in order to get into this solution, I want to change your perspective a little bit about how to view an equation. Okay, so on the one hand, you've got the wave equation. On the other hand, you could consider the following differential operators. So consider this. So I claim that this equation is the same thing as stating that LU equals 0. And so you can see what I'm kind of doing here. So L is a function that takes as an input. It takes as an input a function that's twice differentiable on the upper half plane and has continuous, second partials. I'll try to stay closer to the mic when I'm speaking. Thank you. And has an output continuous functions, right? Because you lose two derivatives, so you start with a C2 or a function is the second partial is continuous derivative, and as an output you have continuous function. So this is absolutely a linear function between two vector spaces. Okay, so the collection of C2 functions is a vector space. You can add two C2 functions together. It says C2. Remember C2, two partial derivatives and the second partial is continuous. So it's a linear function from one vector space to another vector space is continuous function. And if those two vector spaces were finite dimensional, you would in fact be able to build a matrix L, and then you'd be able to find the null space of the matrix and be done. The problem with PDE is that the two vector spaces that you're operating along are actually infinite dimensional. There is no finite basis giving you a linear combination of all C2 functions. There is not even an accountable basis. There's not even an infinite list of functions that lets you, write one function as a linear combination of the infinite list. There is an entire field called Fourier analysis where you take an infinite list of functions like sines and cosines, and you get like as many functions out of that as you can. And you can productively solve for PDE that way. But generally speaking, you have to confront this idea that you're going to operate from one vector space to another. And PDE, in some sense, at least linear PDE is kind of like linear algebra. These bigger vector spaces. And that field of study is called functional analysis, if you ever want to take a class in that field. But for us, I do care about this linear function, but the form of the linear function is simple enough that I'll be able to solve this with another method. But the first thing that I'm going to do in order to solve it is the following. So this function actually decomposes. As the product, or more properly, the composition of two other linear operators. So you could call this maybe L1 and L2. So this, as a linear operator, it's a composition of two first order linear operators. And both of those L1 and L2 should be familiar to you because those have the form of a transport equation. So each of those individually we know how to solve. And that is, in a nutshell, the strategy for solving this equation. To the point where maybe if I were like a brave instructor and I had the ability to walk around and talk to you, I could almost just set you off, say, solve this equation now. Just give it a shot. But no, I'll provide more scaffolding and detail than that. But so from an algebraic standpoint, you can think of just multiplying those things together and it'll work out. But actually take 30 seconds and verify that this equation is true in the following sense. So if you plug in U and then apply operator L1 to U, and then apply operator L2 to the result, you will get UTT minus C UXX. So just to take a moment to verify that. So now maybe you've verified or you've gotten far enough along the way that if you take UT plus C UX and then differentiate that with respect to T and subtract differentiating it, with respect to C times dx, you really will get the left-hand side of the equation. So you're setting that equal to 0. So I want to solve this equation. And I want to take the strategy of solving this L1 and L2 individually, and how should I do that? Well, I want to plug U into L1. And maybe I can call that W. And then I want to assert that L2 of W is equal to 0. So let's think that through. Would that do it? Is that? Well, that is what we would need to do to solve this problem. So if I can solve L1U equals W and then L2W equals 0, that would be the same as solving LU equals 0. That's what I'm trying to get us to agree on. So solving this system of first order PDE is the same as solving the second order PDE. And writing this one down, what do we get? Just by straightforwardly taking L1 of U, that's what I get, and now L2 of W. So I'm arriving at this system of two transport equations as a roadmap for finding a single function U that solves the equation. So take a careful look at it and check me for mistakes or anything like that. Yeah, so W is something you have to solve for. Oh, yeah. Right, so yeah, basically what I'm saying is that if you can solve this equation for W and this equation for U, then you have found U such that LU equals 0. The question was where did W come from? And it's the answer is a little subtle. I think it's a variable in this system that you introduce to allow you to solve two equations just to get one. But in a way, this is the defining characteristic of W, right? It's L1 of U. But you don't just want any W. You want a W that satisfies L2 of U. And you have the problem that you don't know U in advance. So if you did know U, that's W. But you don't know U, so you must solve these two equations. So the first step, in looking at these two equations is I should solve this one for W first, and then plug that back into that equation and solve it. And that is the tack that I'm going to take. All the while, paying attention to these initial conditions as necessary. And the only restriction on your initial conditions is that G should be a C2 function and H should be a C1 function. It's already a derivative, so it can be C1. So the question was, can I repeat what I just said? And the answer is that the initial condition G of x should be a C2 function, and H of x should be a C1 function, because it's already a derivative. Of course, a classical solution U should be a C2 function, so its initial conditions need to have corresponding Okay, and actually, since we know how to solve equations like this, I'm going to make it a class exercise. So take a minute and solve this second equation for W. You will need an initial condition, so I'll give that to you. This initial condition we get to specify, and I'll choose this function later in terms of G and H, but for now, just so we all have the same notation, please solve this equation with that initial condition. So having given you some time to work, I'll show you my solution and we can compare. So first you should write down the characteristic. And since your velocity in this case is minus c, your characteristic is minus ct plus x naught, where x of 0 equals x naught. So the next step is that when you plug in x of t into w and take the derivative, that will be equal to 0. So in other words, w with the characteristic function plugged in, now as a function of t, must be a constant. And so we go through this usual argument where we say which constant is it? And well, so just plug in t equals 0, and then you get that w of x naught 0 has to be w naught of x naught. So since this expression is equal to a constant, you can figure out that constant by plugging in t equals 0 and then using your initial condition. And I remind you that initial condition needs to be specified later on in terms of g and h. But it's not clear to us at the present time like what that expression should be, so we'll determine it later. So right now we're solving this equation with that initial condition. And what I'm saying is we get to choose that initial condition. And then later on, we'll choose it when we are solving the equation for u and w. So we'll choose it so that it matches the initial condition of u. But it's not clear how to do that at the moment. But let us continue solving this equation. So now you try to eliminate the presence of constant x naught by solving for it in that equation. And so you end up with w must be w naught evaluated at x plus ct. So any questions or comments on there?
How did you equate x naught?
So x naught minus ct is x, and x naught is x plus ct. And
I know you said this so many times, but could you quickly go over how you went from how you got the w of x naught minus ct is constant?
right. So the question is how did could I go over how I showed that w of x of tt is constant? And the answer to that is it's this so-called Lagrangian derivative that in general, like if this equation had another term, that would appear on the right-hand side. But since it doesn't, that's 0. But so you're asking me to explain that equation. And this equation says remember by definition, this is the prime derivative of the solution W with x of t plus a. And now we apply the chain rule from Hippocrates. And then we say, so I'll try to keep speaking close to the microphone, and then we say, since dx dt is equal to v because we found the characteristic, and of course in this case v is minus c. I mean, if I ask you to use the method of characteristics to solve a transport equation, yep. Here I'm using it to do something else, so then I think it's appropriate to, explain if necessary. So the question is, this is a question that students often ask is like, do I need to show this when I'm on a test or in homework? And the answer is, it kind of depends on how I ask the question. So like if I ask you to explain the solution to like a first order transport equation or like how to derive it, then you would need to show it. But if I ask you a different problem where you're incidentally using that word, then you don't have to show it. But you do have to know it and be able to show it. That's right.
Could there be a function of, oh no.
Right, so the process for characteristics is you solve the equation on that characteristic line only, but then when you rewrite it in such a way that you're no longer referring to the initial condition, and that gives you a formula for all the initial conditions at once. So it's kind of a neat idea. All right, so let us now solve the other equation. So I'll keep this. And here we're in a slightly different circumstance, so it's no longer true that the derivative is going to be 0, it's going to be equal to w. But when we set up this equation, well, let's just do it. So first of all, you need the characteristic. And in this case, the characteristic is different. It's going to be Ct plus x naught. And now in this equation, u is playing the role that w played before, and now w is given to us. So plugging in the characteristic line x of t into u, and taking the derivative. So just write it all out for the moment. So the process, this time you find the characteristic line x equals ct. Then you realize through the chain rule that ddt u with x of t plugged in is this left-hand side of the equation. Right. And that's now equal to w, but once again, with x of t plugged in, we know that w we know that the solution to w is w naught x plus ct. So I made a substitution. W naught of x plus ct. No, because that's the characteristic line and I've substituted it into the equation. Remember, there's a different characteristic equation for this different equation.
So, okay, so my thoughts looking at this, I'm going to be substituting that characteristic into that x naught. Would, so that if you.
But we're not doing that. We're substituting this for x.
Oh, okay.
Yeah, you're separate. And right, so now we have an equation that maybe we can solve. And so I want to take advantage of maybe the fundamental theorem of calculus. So I want to integrate those sides. So this is a function of t. So what does fundamental theorem of calculus say? I should integrate this from 0 to t. But my variable changes maybe like this. And then I have to add to it the value at t equals 0 to get the constant to be correct. So the value at t equals 0 is u of x naught 0, which is g of x naught. Right, so here I'm applying the fundamental theorem of calculus, so I've got, du dt equals f of t. So u must be the integral from 0 to t of f of t plus a constant. And which constant? So my trick is to just plug in t equals 0, giving me u of x naught 0 equals 0 plus constant. And that constant must be u of x naught of 0 equals u of x naught. Because ct plus ct is 2c.
Even if x naught is dependent on t doing the automatic, we just consider t a function of one variable.
So at the moment, x naught is a constant. It's the initial condition of your characteristic line. And you attempt to solve this equation on the characteristic line. And then you rewrite your formula in a way that doesn't reference that constant, to therefore give you a formula that includes changing the constant. more I think about it, the more I feel like it has to do with our just psychological feeling of wanting X not to be a constant and not wanting to vary it. But yes, that's right. So this works. So we know that this initial condition is chosen arbitrarily. So we can try varying it around. So let's try it. So substituting X naught for its value. We get the following equation. And in some sense, we're done, but except we didn't respect the initial conditions. So I think the next step is to try to choose W naught in such a way that allows us to include the initial conditions and also get like a better form for the equation. And so how to do that? Yeah, the comment was we already used the first initial condition, so we need to introduce the second one. It's already true that ux0 equals qx. I guess I'm stalling this integral concerns thing with it. So what I want to do is maybe change the variable.
You know which. We got the last step.
So we only have one equation and therefore one characteristic. And so the equation was and the characteristic for that equation was this. The question was, how do you know which characteristic to use? And the answer is that it comes from the form of the transport equation. I don't understand the question. Okay. So yeah, I want to work that integral. So let's make a substitution. Let us write tau equals x minus ct plus 2cs. And then just, well, actually, I'll let you do it for a class exercise first. Complete the substitution, calculate d tau, and then rewrite the variable, the integral in terms of tau. Okay, letting you work on that for a second, I'll try to do my own work too. So remember our variables are tau and s. So d tau is 2c times ds. And so now when s is equal to 0, tau is x minus ct. When s is equal to t, tau is x plus ct. Right, and ds was 1 over 2c d tau. Yeah, every time I do this, I'm amazed it works out. And so we're almost there. I mean, returning back to maybe what I perceive is your question, from earlier, and maybe some other people had some questions too, like, why can't you just convert this to x minus ct, and you get the t in there, and then convert it, like why is this good for s, but that stays x naught, and then all of a sudden this is now t? Was that kind of your question? And I see some other people having that question too. And I think what is going on is that, remember, you kind of have to remember what's a constant when. So when you're solving for the characteristic initially, you're picking constant x naught, right? And then at the moment, you are integrating this line. X naught is a fixed constant, and so you perform the integration. But now you want to change that constant to something else, and you're welcome to. X1, x2, x3, whatever. And now that you've got this integral, s is the divariable of the integral, and t is fixed constant with respect to that integral. But the point is, if you change your initial condition to your characteristic, it's still related to t. So you're allowed to make a substitution. So it's solving this equation with x naught fixed, and then varying x naught and using that. I feel like that is really, really valid. Yeah.
If you just get the DDT equals W initial from the genus.
Yeah, this is the so-called, I guess the textbook author called it the Lagrange equation.
And that was when we divided all of it into separate equations.
I mean, it's the way that you solve a transport equation. This is the ut plus v ux, and this is the other part of the equation. So that absolutely came from the equation that we had. So that's the method, and now we're almost there. So let us figure out W naught. So remember, I want to use the equation. The UDT plug in t equals 0 gives me h of x. And I have a formula for u here, so I can just take this derivative with respect to t, then plug in t equals 0, and then equate that to h of x, and that should give me an expression for w naught, I hope. So let's try it. And I'll do a little bit of class participation too. Go ahead and see, can you take this derivative with respect to t? And what formula do you get? So I'll try to do it too, and you can help me out. Let us actually do this term first. Almost. So yeah, the suggestion was negative c g sub t of x minus ct. Well, the issue, of course, I mean, I think that's right, but I wouldn't write it as a partial derivative because remember, g is a single variable function. So what we're literally doing is a difference quotient with t plus h minus with t over h. You plug that in here, it's really, honest to goodness, g prime times that derivative. And here, what about taking the derivative? Here, it's another chain. Right, so I should get w naught of x plus ct times the derivative of the inside function. This is fundamental theorem of calculus with chain rule. Multiplied by c. And then I'm subtracting. So that's the formula, and you can check me, yeah.
Why do we not use the no?
Because w naught is being integrated. So fundamental, like if this were constant and that were t, fundamental theorem of calculus would tell us the answer is w naught of t. But since this is a function of t, fundamental theorem of calculus tells us this is w naught of this function times the derivative of that function. But actually what I've done is I've broken this up into two integrals. One from like 0 to x plus ct, and one, the negative integral from 0 to x minus ct. And applied fundamental theorem of calculus with chain rule twice, and that was the answer. it does matter, but this is, so the question was, does it not matter that this integral was with respect to tau? And then the answer is it does matter, but we're doing everything correctly, right? So this is the dummy variable of integration, and we're taking the derivative as the bounds. So I'll remind you that this is the fundamental theorem of calculus. And then I'll remind you that if this were like a function, you would get something like that due to the chain rule. Okay, and so now, plugging in t equals 0. Oh, right. Thank you. I was wondering where the negative sign was going, and the student pointed out that they cancel, and so it's fine. So we get that and now we're almost finished, but so I mean we're finished in the sense that this is W naught, so we're finished, but you can clean this up a little bit because you can now integrate that derivative. Plus CG prime, thank you. So if you plug this in, uxt is now equal to dx minus ct plus 1 over 2c times the integral of h of x h of tau, d tau, and then plus d prime of tau d tau. But just integrate this according to the fundamental theorem of calculus, and you'll get 1/2 d of x plus ct minus d of x minus ct. And then you'll see the minus 1/2 d of x minus ct takes away 1/2 of this, and you finally get uxt equals 1/2. false. And that's your solution. That's your solution to this initial value problem. And I skipped a little step, but of course you can fill it in. You just integrate this according to the fundamental theory of calculus. You get g of x plus ct minus g of x minus ct times 1/2. There's the 1/2 x plus ct. And then this minus 1/2 gives you the plus 1/2, gx minus ct. So that formula is due to D'Alembert. It solves this wave equation with this initial condition and that time derivative. G is C2, H is C1, and therefore that part of the equation becomes C2 because you can differentiate this twice, once to get back to H, and once again to get continuous. So this is a legitimate classical solution, of which we can discuss more, in the next class period. Yeah.
How do you spell her name?
D'Alembert. And so that's an argument that goes all the way back to the 18th century. So kind of after people had made calculus, there was this Wild West time of trying to better explore physical principles through mathematics. I mean, I guess that still continues. We're still trying to do that today, but back then you could actually use single brain calculus to by yourself get publishable results like this. So, yeah, so thank you everybody for your time and attention. And I'll end here. Take care. Well, it required work back then too.